In the previous video, we saw that light not only had a wave nature, it also had a particle nature. And in fact, the wave nature told us the probability of where we would detect the particle. So it's natural to ask if things that we generally have thought of as particles, matter, also have a wave nature, and is it indeed the same kind of game where the wave nature tells us the probability of detecting the particle? And the answer turns out to be yes. The history of this comes from a French physicist by the name of Louis de Broglie, who when thinking about how was it that atoms only had certain specific energy levels, the idea of standing waves came to mind as a way for how you could only have specific things. And so he decided, well, when we did this for light, we saw that we could relate the wavelength of light to its momentum by h over p. And so de Broglie goes ahead and says, let's just do that for matter. Now you have to use the relativistic expression for momentum, but it turns out that in atomic systems anyway, usually the velocity is low enough that we can get away with not doing relativistic corrections on it. But you do have to do it relativistically correctly if things are moving on. Anyway, this is the de Broglie. The name is spelled D-E space B-R-O-G-I-L-E. I'm sure I'm butchering the French. That's my best attempt at it. This is the de Broglie wavelength associated with the particle. And then he goes ahead and says that the wave nature should dictate the probability of finding a particle somewhere. And so it turns out that, believe it or not, the experiment to confirm de Broglie's prediction had been done about a decade earlier, but the experimentalist in question didn't realize what he had. He had fired electrons on nickel, and he saw a pattern that looked like an X-ray diffraction pattern. When we did Bragg diffraction in the last video, he has a certain diffraction pattern for shining X-rays on nickel, and he got the same kind of thing when he shot the electrons at. And he thought that was weird, and he couldn't explain it, and so he sat on the result, but he didn't throw away any of his notes or his photos. When de Broglie's prediction was published, it came to his attention, and that rang a bell from that experiment he did about a decade earlier, dusted off all of his notes, analyzed it, and saw that, yes, the electrons would diffract in exactly the same way that X-rays diffracted on the nickel crystal. The images basically look the same. So the experimental validation came out very quickly. Now, just to give some sense, again, just to connect this to our everyday life, yes, you and I, when we're walking around, we have a de Broglie wavelength. So let's just go ahead and figure out what would the de Broglie wavelength be for a person with 100 kilogram mass walking at 1 meter per second. Well, this is clearly classical, so we can say lambda is equal to h over p. This would be h over mv here. So this is 6.626 times 10 to the negative 34 joule seconds over 100 kilograms and 1 meter per second, like so. So this turns out that this is going to be 6.626 times 10 to the negative 32 meters. So yes, technically when you walk out the door, you single slit diffract through the door. But for a typical width of a door, this means that your central maximum is going to be something like on the order of about 10 to the negative 31 radians or so, which means you are totally never going to notice that you single slit diffracted through the door. So it turns out here, because for macroscopic objects, the de Broglie wavelengths are ridiculously short, the wave nature doesn't really show up, and we recover our classical physics. However, on the other side of it, let's say you take an electron and you accelerate it through a large voltage difference. Then you'll have a really short de Broglie wavelength. And this is in fact the basis of how an electron microscope works. You can go ahead and shoot these electrons at, and because they have this wavelength, it'll behave just like an optical telescope, but the difference is that you can make the wavelengths shorter than you would in a typical optical telescope, which means you can have higher resolution images, because remember, the resolution goes as how many waves you can fit across the aperture. So if you can make the wavelength shorter, you get higher resolution than you can with visible light. So that's a good application for that. Okay, so to get our feet wet with thinking about de Broglie wavelengths, one of the classic problems that we look at is the particle in a box. And it's just as exciting as you think it would be. So I'll start with the classical picture of it. So the classical picture is, I got a wall here, I got a wall here. We'll say that the walls are separated by some length L. And classically, we just say I've got a mass, it's going at some velocity, and it's just going to rattle back and forth within the box. So classically, it could be anywhere in the box. However, what the matter waves are going to tell us is that we can only have standing matter waves. And again, the wavelength will dictate the probability, the wave property will dictate the probability of locating the particle. So in the matter wave picture, what we're going to be requiring is that I have a matter wave. So just like when we did standing waves with like a string that was fixed at both ends, it turns out to be the same kind of thing. One solution, the lowest possible state, is that we're fixed on both ends, and then the next available solution is that we fit a complete wave in versus half a wave, then a complete wave, and then the n equals 3 case is where you could fit in a wave and a half, and so forth. Just like when we were looking at a string tied on both ends back in mechanics. I'll spare the algebra, but what this gets is that we can only have certain energy levels for our particle in a box. It turns out to be h squared over 8m L squared n squared, where n is 1, 2, 3, no 0 here, 1, 2, 3, and so forth. So it turns out that these are our only possible solutions. So we can only have certain energies for our particle in a box. Now, how can we interpret that? So what I've got here is our solution for the particle in the box. The blue is the sine wave, the half of a sine wave that we can fit in for our lowest possible state. The gold that you see there is the square of that. It turns out that the probability of detecting the particle goes as the square of the amplitude of the matter wave. This is an analogy to light, where the probability of detecting a photon would go as the intensity, which went as the square of the electric field strength. So exactly the same idea here. So for n equals 1, what we'd say is that there's a pretty good probability that if we look in the box at a particular moment, we'll see the particle in the middle, with lower probabilities as we tail off to the side. The next available state will be one where we can fit an entire wave into the box, and then the probability of detecting the particle will be high at about around about a quarter of the way over. You'll never find it at halfway, high again at about 3/4 of the way, and falling off in between. And then for the n equals 3 state, same idea. The solution is the wave is the blue, the probability is the square of the wave, the gold here. And again, we can see that we're highly likely to find the particle here, here, or here. We'll never find it there or there, and anywhere in between. It's somewhere in between. Now, how does this correspond with classically, if I just imagine, say, a ping pong ball rattling around inside a box, and say, hey, I should be able to look in and basically see it anywhere. Well, here's how we interpret that, because this does actually happen for a ping pong ball inside a box. And that is as we get to higher and higher quantum numbers. So here, let's say this is already the n equals 15 case. We can see that you're really likely to be here, 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 here. There's an awful lot of places where you're really likely to be. And as we keep cranking up the quantum number, the places where you're likely to be get more and more and more and more finely spaced. Now, my computer program that's drawing this starts to lose it if I go past n equals 20. But you can imagine if we take this up to like n equals 1 billion or something like that, what this means is, here we've got 20 different places we could find the particle. If I'm up to n equals 1 billion, some large quantum number, then I've got 1 billion places I can find the particle. And we're getting to a point where I can't really tell that there are places where the particle isn't allowed to be. And so that's how we square this with classical physics. So let's go ahead and take a look at this both for a classical situation and a more typical quantum mechanical situation. So I was mentioning confining a ping pong ball to a box. So let's go and put a ping pong ball in a 1 meter box. So I want to know, what is the slowest speed what is the slowest speed that our ping pong ball can have? Because it can't be 0. The lowest available energy isn't 0, so it can't just sit there. But how slow, what's the slowest it can go? And we'll see what we get from that. Okay, I am enough of a dork about this that I actually looked it up, and according to the International Table Tennis Federation, they require that the mass of a ping pong ball be 2.7 grams. So, okay, let's work with that. I'm guessing that our speeds are going to be really slow, and so I'm just going to go ahead and say that I can approximate my energy as 1/2 mv squared. Now, if I solve this and I either get an answer much faster than the speed of light or even a decent fraction of it, I'll curse my luck, go back and do from relativity, the gamma minus 1 mc squared for the kinetic energy here. But anyway, 1/2 mv squared, and I'm going to equate that to a result, h squared over 8 ml squared n squared. All right, so we can rearrange this bit here. I can get that v squared. Well, let's see, this 2 cancels that. That's going to give me a 4. And I'm otherwise going to get h squared over 4 divided by m. I'm going to get m squared in the denominator, l squared, n squared. Take the square root of both sides. I get that our speed at any quantum number is going to be h over 4 m ln. Okay, since I want the slowest speed, that would be the lowest energy state. So we'll just go ahead and put in n equals 1. So for my ping pong ball, this would be 6.626 times 10 to the negative 34 joule seconds, Planck's constant, over 4. I'll have to turn my 2.7 grams to kilograms, so it'll be 0.0027 kilograms. And we said that the ping pong ball is sitting in a 1 meter box. And I will substitute in 1 for my principal quantum number because I want the lowest possible energy state. I get that the slowest this ping pong ball can go, it can't go 0. The slowest it can go, just sitting in a 1 meter box, is 6.13 times 10 to the negative 32 meters per second. Now, there is no way that you'll be able to tell practically that that ping pong ball is moving versus completely stopped when we're talking about a speed of 6 times 10 to the negative 32 meters per second. So that's how we go ahead and tie that into classical physics, where we expect that the lowest possible energy state would be a dead stop. The answer isn't a dead stop, but it's pretty darn close to a dead stop. But now let's repeat this for an electron in a hydrogen atom. And the way we can approximate this is to say that we have an electron. The width of a hydrogen atom is about 0.2 nanometers. So we'll say for an electron in a 0.2 nanometer box. And now let's see what we get here. Again, I'm crossing my fingers hoping that it's a classical speed so I don't have to do the full-on relativistic calculation. Anyway, I can just plug literally into the same result, again keeping the quantum number of 1. So 6.626 times 10 to the negative 34 joule seconds over 4. Now the mass of an electron is 9.11 times 10 to the negative 31 kilograms. Our box is 0.2 nanometers. That's 0.2 times 10 to the negative 9 meters. And again, we'll multiply by our quantum number of 1. And we get 9 times 10 to the 5th meters per second, which is fast. I mean, that's, you look at that and you're saying, wow, that is 90. Our semi-classical electron is apparently moving at somewhere around 900 kilometers a second in an atom that's only 0.2 nanometers wide. So this is why we talk about electron clouds, because there's absolutely no sense in being able to localize it. Now, I am sweeping some stuff under the rug here to be clear. The electron cloud picture is, again, just dictating the probability of where I'll look at the particle. And it's not even really fair to talk about the particle moving because of quantum mechanical issues of connecting one observation to the next. But at least for just an idea to hang our hat on, that makes sense. Now, if we compare the speed of light is 3 times 10 to the 8 meters per second. So this is a lot lower than the speed of light. So in retrospect, we can say, yeah, we can get away with saying that it's going at a classical speed, thankfully, even though it's darn fast inside a small thing. Now, is this answer absolutely correct for our electron? Well, for one thing, I'll say it's even kind of a bad question to say how fast is it going, again, because of more complicated quantum mechanical issues that are beyond the scope of this treatment. But there's also the issue that we'll have to do a more careful analysis to take into account the fact that, we have an electric force. It's not really a box, but it turns out that the correct answer isn't that far off. So this particle in a box thing gets used by a lot of people just to estimate answers when they don't want to do a more tedious calculation. All right. So now let's say that we were confining an electron in our box or something like that. Then what winds up happening is we can go ahead and make our electron change its energy. So let's say the mass of the electron, the width of the box, and everything is such that, just to make this nice and concrete, that our lowest energy state, E1, we'll say is 10 eV. So then that's 0 eV there. Now what we'll be doing is we'll be drawing something that atomic physicists call a term level diagram. This is just where we draw lines at the, it's not really a graph or anything, we just draw lines at all the allowed energies. So since the allowed energies go as the square of the quantum number, the second allowed energy would be 40 eV. The third allowed energy, again going as the square, would be 90 eV. And if I were to take this up, the fourth one, sorry, this isn't going to be drawn really well to scale, would be 160 eV. And let me at least make this line there. We'll do that just to make it a little better anyway. This would be my n equals 4 state. Now there's going to be more going on, but the way that you wind up getting, say, if we have an electron in our box, the way we can change, if our electron is in the ground state, another name for n equals 1, say I wanted to go to the n equals 3 state. The way I would have to do this, I'd have to shine a photon at it to provide energy. And the required energy that this photon would need to be would be the difference in the energy. So in this case, E3 minus E1. So this would be 90 eV minus 10 eV would be 80 eV. Similarly, let's say I had an electron already in the n equals 2 state, and it decides to go down to the n equals 1 state. How that happens, we'll get into that later. But let's say my electron wants to go down here. The energy of this photon, again, would have to conserve energy. This would be E2 minus E1. So this would be 40 eV minus 10 eV would be 30 eV. If I need to know frequencies or wavelengths, I can just remember that the change in the energy would be equal to the h times the frequency of the wavelength, or hc over the Planck's constant times the frequency, or hc over lambda, where lambda is the wavelength. And so I could do that to solve for the wavelength of the electron. Now, real atomic systems don't look like this, and there's going to be some additional complications coming in the form of what are called selection rules. But the whole point here is just, if I want to go from one energy to another, I need a photon of exactly the right energy to make that happen. And if I go down, I emit a photon of exactly the right energy. This will come into play when we think about spectroscopy. All right, so to better motivate, I hope, the Heisenberg uncertainty principles, is where I'm going here. I'm going to present, and I'm not going to make any kind of a deal about being able to apply this at all. I'm going to present something called the Schrödinger equation. So this is due to a German physicist by the name of Erwin Schrödinger. So de Broglie's matter wave ideas were great ideas, and they got expanded by other people like like Niels Bohr and folks like that. But it turned out that the full technical understanding, it took a while to get fleshed out, and most of this is due to Erwin Schrödinger. Now, I'm going to write something that looks incredibly ridiculously scary, and I'm not even going to explain what the math symbols mean, but I will talk about physically what each term means. So, but I figure this is one of the key equations of quantum mechanics. You should at least see it. So, the Schrödinger equation, so this thing that looks like a funky pitchfork, this is a capital Greek letter psi. 8 pi squared m. That should look familiar from our particle in the box. Again, the true derivation is coming from a bit of a different place, but the idea is right. All right, so I am just plain going to assert with zero proof that this thing is a wave equation. These funky pitchfork things get called the wave function. So this is the generalization of de Broglie's matter waves. We just give it the name the wave function, but still the same idea. We solve for the wave function, we square it, it gets us the probability of where we will detect the particle. But the physical meaning of this is actually kind of interesting. This term here, and again, I'm not explaining any of the math of this, I just want to talk about the physics. This term here is actually the mechanical energy. Technically, it's a thing called the Hamiltonian, but in virtually any situation anyone would ever care about, that's the same difference as the mechanical energy in a quantum mechanical system. This term here turns out to be the kinetic energy, and this term here is the potential energy. So it turns out that this is actually a statement that the total mechanical energy is equal to the kinetic plus the potential. But Schrödinger was able to take this idea and work it into a wave equation where we could solve for this wave function and get our matter waves. And everything works out. You wind up getting the exact wavelength that Louis de Broglie calculated. If you do you can do double slit diffraction on your electrons, and it all does the right thing, and they land exactly where the square of the wave function would predict. Just like if you shined light through a double slit, they land where the square of the electric field strength would be. So like I said, I'm not going to explain this equation at all, but I just want to say it's an energy conservation statement, and Schrödinger was able to couple energy conservation into a way to describe these matter waves. Now, what I'm really going to use this for is when any book motivates Heisenberg's uncertainty principle, it tends to they tend to take a few too many liberties. So this is due to the German physicist Werner Heisenberg. And a lot of books and everything, they give all sorts of motivations where they say, in order for me to measure something, I have to look at it. And if I look at it, I change it, and that creates an uncertainty. Well, it is true that if you look at it, you change it, and that's actually a key idea in quantum mechanics. But that motivation to build up the uncertainty principle, I don't think is fair. Instead, it's more of a statement that if I write something, like say I've got some wave that looks like this, it's not a true wave, it's just sort of a wave-ish thing. How would you attach a frequency to this? Well, it turns out that you can give it a value, but then you have to say that there's a spread of values. And it turns out that just like position, that we would have this kind of relationship between the width, the period of the wave and the frequency. There's a similar relationship with our matter waves between position and momentum. So, from fundamental considerations of the Schrödinger equation, in other words, it's just fundamental properties of space itself, you have a constraint. You cannot simultaneously measure the position and, say, the x component in this case of a particle to arbitrary precision. It turns out that the product of the uncertainties, so this is the uncertainty in position, and this is the uncertainty in momentum. This product of uncertainties must always be greater than Planck's constant over 4 pi. If you look in some places, they might write it like this, h bar over 2. The bar notation in physics means divide by 2 pi. So this is take h divided by 2 pi, then divide by 2 again. Same thing. Since I'm not really introducing h bar, I'm just going to write it like that. But I'm just putting that out there in case you've seen that somewhere else. And if we remember from relativity, we saw that energy and time are also, energy was the time-like component of momentum. So there's a similar relationship between the uncertainty in the energy, your measurement of the energy of a system, and the time that you're measuring the system over. And that turns out to be the same relationship. So both of these are statements of Heisenberg's uncertainty principle. Now, for most practical things, the uncertainty in position and the uncertainty in momentum will usually both be sufficiently large that'll way overwhelm this. However, in atomic physics, there is a trick you can do called optical molasses. By using very carefully tuned laser beams that take advantage of Doppler shifts and stuff like that, you can actually reduce the momentum of a particle to very small levels. And then you'll find you'll actually get to a certain point when you get the uncertainty and momentum really small. Suddenly, the uncertainty in the position starts going up, or vice versa, depending on how you're setting up the experiment. And it turns out that yes, this is a thing. So you can never simultaneously be able to measure both the position and the momentum of something to arbitrary precision. There's always a little bit of slop in that. And this is a fundamental property of nature itself. It's not a statement about measurement technology or anything like that. This is a statement independent of any technology that currently exists or will ever exist. But there are some weird side effects of this. One of the consequences of the uncertainty principle is something called virtual particle pair production. So it turns out that space isn't as quiet as you might think. Because if we go and look at this delta E, delta T is greater than h over 4 pi. We can flip this around and say that if some event had this much energy but took less than this much time, you would not be able to detect that it happened. And so what is totally possible is just at some random point in space, suddenly, say you make an electron and a positron, the antimatter dual of a positron. Now, to do this, to make an electron, you need 511,000 eV of energy. So to make the two of these, you need a little over 1,000,000 eV of energy. This pair of particles will poof into existence, and then they'll pop out of existence. Now, where did the energy come from to do that? Well, the usual phrase we say is it borrowed the energy from the vacuum. The idea is that nature can steal energy from the vacuum as long as these particles annihilate in such a short amount of time, a time less than what's set by this scale here, such that you can never detect that the particles were made. Now, when I say never detect, I mean never detect directly. It turns out that we do know that this sort of thing is happening all the time. And this is because, for instance, if we look at a hydrogen atom, here's my proton, there's my electron in the hydrogen atom, there will have a certain electric interaction. Now, these virtual particles will come into existence, and when they do, during the very short time that these pair of particles exist, the positron will be moving over towards the electron, and the electron that got made will be moving over towards the proton. Let me color these gray so that we know they're what we call virtual particles. And these are going to be destroyed so fast that we literally cannot detect the particles. However, it turns out to properly get the correct experimentally measured energy for the electron orbiting the proton in the hydrogen atom, you do actually have to take into account the electrical interaction that this pair of particles had. So although we cannot directly see the particles being made, we can see the indirect side effects of that happening. Another example of this is a phenomenon known as the Casimir effect. And so here at the Casimir effect, the idea is if I put two plates absurdly close to each other. How close? I'm glad you asked. Closer than the width of an atom. Now, if I get two plates put absurdly close to this spacing starts to limit because we need to have a standing matter wave. This limits how many virtual particles we can create because they have to fit the standing waves of our matter waves. So we wind up having fewer virtual particles inside the plates, and we have more virtual particles outside the plates, just because there are more possibilities for how to make them. This winds up creating a pressure on the plates that pushes the plates together. And we have measured this in the lab, and it happens. So again, even though we can't see the virtual particles themselves, we can see the side effect of the fact that more of them are being created outside the plates than inside. This also was how Stephen Hawking was able to figure out that black holes had to dissipate. So the issue here gets back to some issues of thermodynamics. So Hawking radiation. So Hawking and Roger Penrose were corresponding with each other. Penrose was one of the early people working on black holes. And there was sort of a debate going on. And one of the things the theoreticians are always worried about is respecting the laws of thermodynamics. Because if you'll recall, the key assumption of thermodynamics is merely that particles interact. Not even how they interact, just that they interact. So when you're building a system on such minimal assumptions, if any physical model doesn't respect the laws of thermodynamics, then you kind of have to go back to the drawing board and rethink it. So what I drew here, I can't draw a black hole, but I can draw a boundary for what's called the event horizon of the black hole. This is the point where if you get too close to a black hole, you won't ever be able to get back out. It's like, you get to like a river, where you get to some point where the river goes so fast you can't swim upstream anymore. Same sort of idea. Gravity gets to be so strong that you get pulled in and you can't go back out, not even light. So Hawking was worried about whether this respected the laws of thermodynamics. And he basically posed a question. He says, let's say I smash a teacup. If I smash a teacup, I've increased the entropy of the universe because a smashed teacup has higher entropy than an unsmashed teacup. But then what if I take all the teacup shards and chuck them inside the event horizon of a black hole? Now I can't see them anymore, right? So did I just suddenly cause the entropy of the universe to decrease and thus violate the second law of thermodynamics? So Penrose and others started doing a bunch of calculation on that, and they worked out that no, actually it's all okay, because when you chuck the teacup shards in, you increase the mass of the black hole, which turns out to increase the radius of the event horizon, and they were able to show that the entropy of the black hole can be measured by the radius of the event horizon. So everything's good. You toss the teacup shards into the black hole gets bigger, we know the entropy of the black hole went up. But if something has an entropy, it also has to have a temperature. If it has to have a temperature, it also has to black body radiate. And so Hawking was wondering, how the heck can that happen? And it turns out the answer is these virtual particle pairs. Usually it's going to be photons, not electron-positron, but same idea. So we make a virtual pair of particles. But they happen right next to the event horizon. One of them falls into the event horizon. One of them's energetic enough to fly away forever. This is a problem. This particle is going to last longer than the amount of time which you have to put the energy back in order to satisfy the Heisenberg uncertainty principle. What Hawking was able to show is that, okay, that means you have to actually find the energy from somewhere to make good on having made this particle. And Hawking was able to show that the energy actually came from the black hole. So it turns out that black holes do black body radiate, although they're very cold. So right now in the current age of the era, the epoch of the universe itself is warmer than the black holes. So there's actually more radiation falling in than going out. But black holes are black body radiators. They do emit light very slowly. The energy to do that's coming from the black hole. And so eventually the black hole will dissipate. All right, so that's a lot of fun applications, but let's just go ahead and take a look at something like, let's say, what is the smallest box that I can put an electron in and know for sure that the speed is no more than 10 meters per second. All right, we can do this with the uncertainty principle. So to estimate something like this, we can say, well, so we'll start with the uncertainty principle and say delta x, delta p sub x has to be greater than or equal to h over 4 pi. The most uncertain I can be in position to make my momentum as small as possible, and thus my speed, will be L. The most uncertain I can be in my momentum is the value of the momentum itself. So that'll be h over 4 pi. So since I'm trying to get the slowest speed, I can get rid of the greater than and just shoot for equality. And so this will give me that v is equal to h over, L. I want L. L is going to be equal to h over 4 pi mv. Okay, h is 6.626 times 10 to the negative 34 joule seconds over 4 pi times my mass is 9.11 times 10 to the negative 31 kilograms. And I said 10 meters per second. Turns out that my smallest possible box, I can do that, is 5.79 times 10 to the negative 6 meters. Now, by comparison, an atom is on the order of about 10 to the negative 10 meters across. So this is substantially larger than an atom, even though it's still small compared to macroscopic things. All right, so a few other weird things that I'll present from this kind of analysis. One of them is antimatter. So it turns out that the Schrödinger equation is non-relativistic. To properly incorporate relativity into it, you rely on a different thing known as the Dirac equation, which was created by the developed by the British physicist Paul Dirac. And I won't get into it other than to say that the Dirac equation predicts that every particle has its antimatter dual, which is a particle of the same mass but the opposite charge. Some particles, like the photon, are their own antiparticle. But yeah. And yes, just like they're saying in Star Trek, if you have a particle and antiparticle meet, you can have them annihilate and produce two photons of the same energy. So for instance here, a positron is a positively charged electron. It is the antimatter dual of the electron. So let's say I have a positron and an electron come together, we'll say nearly at rest. When they come in order to conserve momentum, I'm going to have to shoot out two photons back to back. And so what I would like to know is, what is the wavelength of these photons? I can do this by conserving energy. The energy, I have two photons, so the energy of a photon is hf, and I have two of them, and they'll be identical photons. The available energy will be the rest energy of each of these particles. Well, this has the exact same mass as an electron because it's the antimatter dual of it. So I have two particles, each with rest energy mc squared. So I can cancel the twos. Yay. And then I can also go ahead and say that F is c over lambda, just like before, so hc over lambda equals mc squared, or the wavelength of my photons will be hc over mc squared. I can go ahead and cancel a c and be left with h over mc. So putting in 6.626 times 10 to the negative 34 joule seconds. Mass of the electron is 9.11 times 10 to the negative 31 kilograms. Speed of light 3 times 10 to the 8 meters per second. And I get that the wavelength is 2.42 times 10 to the negative 12 meters. or 2.42 picometers. This is firmly in the gamma ray. This is way shorter than X-ray. This is in the gamma ray end of the spectrum. But we have made these and we have detected them. One other phenomenon that comes out of analysis of the Schrödinger equation and the wave-like nature of a particle is a phenomenon known as tunneling. So let's say, like, I have a pair of plates that create an electric potential difference such that the electric potential energy at some spot is greater than the for some region here, that this is greater than the available total mechanical energy. It turns out that because of the wave nature of this is like when you have a rope that changes thickness. Some of the wave will go forward and some of it will go back. Same kind of idea here. We can look at the matter wave here. And then in this region here where the total mechanical energy is less than the potential energy, so classically it can't be here. It turns out that you can have a solution over here. And so what happens is that you can have an electron here where it's classically allowed. It's classically allowed here. It's not allowed here. It doesn't have to be an electron either. It can be just about anything. It turns out that there is some probability that I can look at it here, and then later it'll be there. Now, you might be worried about, wait, you're saying that I might look and see it here, and yeah, but it turns out that if you calculate the uncertainty using the uncertainty principle, the uncertainty in the position will be so large that you can't exclude that it's somewhere where it would be classically allowed. So you can never definitively say that a particle is here, but it could be here, and then later I could look and it could end up over there. This is called tunneling. This actually happens all the time. You can see it in certain molecular systems, and there are semiconductor devices known as Josephson junctions that actually rely on this phenomenon. So this is a thing that does actually happen. And you can use this to do what's called scaling tunneling microscopy, where the idea is you bring a probe really close to a material and you can have electrons actually tunnel from the material to the probe. And it turns out that the probability of the tunneling depends very sensitively on the width of the gap. So by doing this, you can actually notice atom-sized bumps and dips in a surface. So if you've ever looked at STM photos of like the surface of silicon or something like that, and you see these little bumps, they are actually picking up the electron clouds of the silicon in there. All right, so that is our preview to our introduction to thinking about matter as a wave. And again, it's the same deal. The wave property dictates the probability of detecting the particle. In future videos, we will start to extend this more specifically to spectroscopy and atomic systems. So we'll catch you over there.